Hi everyone. Before starting, let me introduce myself and our group. I am Rafat, project manager, and we are 4 robotics students. Me, Rafat, Fu, Temu, and Mohammed. The project we have been working on for past 4 months is called Data-Driven Robot Model Learning for Robot Simulation and Control. We're quite excited to present our results. On the last slides, we have the demo of the system on the simulation and on the actual mission. Now, let's talk about our project in more detail. Data-driven models have gained a huge traction in robotics. Now, we apply recent developments in this field to hydraulic manipulator. Hydraulic itself is difficult to model. Modeling and controlling hydraulic manipulator is trickier and more time-consuming. Our project aims to tackle this problem with Gaussian processes and neural networks. We are using Gazebo simulator on top of ROS2 to facilitate easier development and reproducibility. Our Gaussian process model of an hydraulic actuator takes the current position of a joint and the valve command as an input and predicts a discrete change in state with a confidence on the output. If you look at the bottom plot, you can see there are two curves. Blue one is an actual change in state, and the orange one is a predicted change in state. Similarly, on the top plot, blue one is an actual position, while the orange one is a predicted and integrated Gaussian process output. Modeling in itself is enough for creating a more realistic simulation environment. As a next step, controller can be trained based on this model to control the manipulator itself. We have used neural network architecture to train the controller for reaching a goal destination. By feeding a goal position and the actual position to the controller, and using a GP model to predict the next state based on neural network output, which is a valve command, controller can be trained. For that, a suitable reward function has to be chosen. Controller uses linear model with hard-turn activation. Input to the model is the difference between the current state and desired state, and the output is a valve command. You can see the policy plotted on the left. X-axis is a state error, while the y-axis is a valve command. For negative errors, valve command is positive. For positive errors, it's negative. And when the error is 0, meaning goal state has been reached, valve command is also 0. Now on the right, you can see the reward function, which is solely a function of state error, nothing else. Sole objective being to reach goal as fast as possible. Issue with that is that it doesn't care how it reaches it, and as a result, you end up getting aggressive policy. As you can see from the policy plot, see how the command stays at maximum value for a long time. Here you can see the video of the model in action inside the Gazebo simulator. Positions are published to boom post topic, and the model generates and sends commands to the Gazebo simulator. And here is the model executed on the actual machine. Thank you for your attention. Hope you enjoyed this presentation.